Waterfalls. Humans are intrigued by the beauty of waterfalls. We find them breathtaking and are willing to travel hundreds of miles simply to bask in their mist. In North America, two waterfalls, Yosemite and Niagara Falls, draw the largest number of visitors every year. Yosemite Falls, at 740 meters, which is 2,428 feet, is the tallest waterfall in North America, and Niagara Falls has the largest flow, with 168,000 cubic meters of water falling every minute. Niagara Falls and Yosemite Falls have been around for thousands of years, but they will not last forever. Gradually, over time, both waterfalls will wear away, destroyed by the rivers that created them. All waterfalls are eroded by the water moving over their rocks, and the edge of any falls will eventually become less steep and move slowly upstream. In the last 12,000 years, Niagara Falls has moved about 11 kilometers, which is about 7 miles, up the Niagara River. But recently, Niagara has started eroding more slowly. Do you know why?
I'm here in New York State visiting Niagara Falls, and right across the river is Canada. Isn't that an awesome sight? Do you realize the energy that water possesses? Draining 4 of the Great Lakes, the Niagara River reaches the crest of the falls, traveling more than 40 miles per hour. Then it falls 176 feet over the American and Bridal Veil Falls, and 167 feet over the Canadian or Horseshoe Falls, more than half the length of a football field. But do you know the force of that water actually changes the shape of the falls?
This is the birthplace of Niagara Falls at this cliff known as the Niagara Escarpment, which started a little over 12,000 years ago. And since that time, the falls has carved out the Niagara Gorge, and it's moved back over 7 miles to its present location.
The falls migrate upstream because of the differential strength of the rocks that underlie the region.
At the top of the falls is an erosion-resistant rock called dolomite, or dolostone. Water going over the falls is able to undercut the softer shale and sandstone layers below, creating the potential for collapse. Tiny fractures in the dolostone, called joints, allow water to seep in. When the water freezes, it expands. The dolostone cracks, and these rocks break away and wash down into the plunge pool below, moving the falls back another notch.
The amount of erosion at the falls has lessened over the thousands of years. Originally, it was 3 to 6 feet a year, and its history eroding back to its present location. Today, it's less than a foot a year.
One of the main reasons for that is the 1950 treaty between the U.S. and Canada, which allows both countries to divert water above the falls for the production of electricity. To study the rate of erosion, the American Falls were actually stopped in 1969. A coffer or earthen dam was built to reduce the falls to a trickle. Rocks were reinforced, but in the end, it was decided to let nature take its course.
Since we seem to have committed lately to letting the falls evolve naturally, what's probably going to happen with time is that the falls are going to continue to erode back upstream. Eventually they'll join each other, and for a while we might have one single incredibly large fall going across the entire river. And we might even see someday 10, 20,000 years down the road a waterfall coming directly out of Lake Erie.
One of the main reasons for the drop in erosion of Niagara Falls is the electrical plants above the falls. These power plants divert the water to control the amount that goes over the falls at any given time. This reduces the rate of the water and erosion of the falls. Should scientists and engineers be able to stop the flow of the falls for human electricity consumption? Should the waterfall be able to take its natural course and not be stopped by humans? What source do you get your electricity from? Is it some renewable source? Engineers and scientists have created a project where they will create more energy for homes and businesses in the surrounding area of the dam. Engineers created a tunnel to pump water under the dam in order to regulate how much water they use on a daily basis for electricity. Once it is finished, the tunnel will be open to divert 500 million gallons of water every hour. This process will allow the water to be used to boost the power supply by over 25%. It will help light the streets of Toronto and power over 160,000 homes. Have you ever visited a dam? Could this type of energy be used in an area near you to help power your town or home city? What would be the best type of renewable resource used in your area for electricity? Do you feel humans should slow the natural erosion process of the falls? Or can this new technology provide others with ideas on how to obtain their power?
Niagara Falls is a geological wonder. But it has a weak spot that will eventually lead to its destruction.
The key thing here to what's happening right here is the presence of this very soft rock. It's an ancient mudstone, very soft. It's called a shale. And it supports that cap rock up there. But the shale is very easily eroded, so the falls are always moving backwards.
12,000 years ago, there was no waterfall at Niagara. The face of the falls was 7 miles downstream, right on the shore of Lake Ontario. As the water fell over a 150-foot drop, it started to eat into the mudstone at the foot of the falls. It eroded the soft rock at the bottom until the harder cap rock above collapsed. This way, the edge of the falls ground its way backwards through millions of tons of rock to where Niagara is today. And the process hasn't stopped. Every 10 years, the falls move back 1 foot.
All waterfalls recede, but none anywhere in the world are moving back as fast as this one. It's slowed up now because water's taken off for hydroelectric power. But in another 20,000 years' time, those falls will have gone.
Until this happens, engineers want to make the most of this natural wonder. To meet the increased demand for electricity, they need to get more water to the power stations. The plan is to dig a gigantic feeder tunnel right under the city of Niagara Falls. The tunnel will be twice as wide as New York's Lincoln Tunnel. A job for the world's largest digging machine, Big Becky. Soon, billions of gallons of water will rush through here, but not a drop can escape. Today, engineers are installing a waterproof membrane that will cover the whole length of the tunnel.
If the fresh water being delivered through the tunnel were to get into that surrounding rock, it would cause the rock to swell and damage the concrete liner.
The plastic membrane is just a fraction of an inch thick. The workers must now cover it with over 700,000 tons of concrete, all without making the tiniest tear.
This truck is coming from our drop shaft 100 meters down from the surface. There's 17 trucks per pour. Concrete mixer is getting placed onto the sliders. It's going to get slid over to the remixer. It's going to get pumped onto the floor. We're about to pump a few more meters of concrete into the line before we close the hatch and switch to our final injection line. Go ahead, start the pump.
Each pour can take up to 7 hours. The team will work 7 days a week to line the remaining 2.5 miles of the tunnel. Then they'll hook it up to the river to feed in nearly 500 million gallons of extra water every hour.
A year from now, when the tunnel's complete, you wouldn't want to be standing here because there'll be 500 cubic meters per second of water flowing through this area.
The new tunnel will boost Niagara's power output by over 25%. It will help freeze the ice at the Air Canada Centre and keep the players in the spotlight. It will light the streets of Toronto and keep people warm. All in all, the water from the glaciers can power an additional 160,000 homes.
Waterfalls are one of the most powerful agents of erosion. But what other types of erosion can make a big impact? Take a moment to think about your home. What types of trees, grass, and soil exist there? Now think about your school. What do the grounds look like? What about the fields or even the concrete? Erosion and deposition depend greatly on the landscape and climate where they happen. While you may not live next to Niagara Falls, the landscape around your home, whether it is a forest with a river, a concrete-filled city, or the slope of a mountain, it contributes to the way erosion and deposition change the land. All of these properties affect how the water, ice, wind, and gravity change the landscape. Scientists research the ground we live on to better determine what has happened in the past and what might happen in the future. Just as the scientists in the videos study Niagara Falls, others study mountains, glaciers, and tectonic plates to learn about the past and explore the future. Engineers use Niagara Falls as a major agent of erosion to create energy. Similarly, they can harness wind, water, and heat from the earth to meet human needs in a sustainable way. How can different types of erosion and deposition affect you in a positive way? Has erosion ever affected you in a negative way? Maybe in the form of ice, rain, or extreme weather?
These days we know an awful lot about hurricanes, how they're born, how they grow, where they go, and who should flee. Mostly thanks to technology that keeps our eyes on the sky. But Jeff Donnelly is a hurricane hunter who happens to be a geologist, and so he is looking the other way.
We're able to determine the hurricane activity by basically taking long core samples and looking at deposits that were washed in during hurricane events.
With help from the National Science Foundation, Donnelly is augering into this Cape Cod marsh to see what happened here in the BM era. That's before meteorologists, way before. Cores like this are nature's archives. You just have to know how to read them, which Donnelly does in his lab at the Woods Hole Oceanographic Institute.
So this grass is what we were standing on when we took the core, and as we move down, we're basically moving back through time. You get this light layer at around 40 centimeters, and if you feel it, you can actually feel all the coarse grains of sand that were transported from the beach into the marsh during the storm event. And it probably dates somewhere to the early 1800s or late 1700s. Then as we go further back down the core, there's another light layer here, so it's probably 800, 900 years ago. If you feel it, it's also got some sand in it as well, providing evidence of a storm that we knew nothing about before we started doing this work.
But there is more than meets the eye in these core samples. Donnelly uses a sophisticated scanner to determine the precise dates of ancient storms and thus see long-range patterns. Donnelly is also exploring the link between climate change and hurricanes. Does a warmer planet with warmer oceans mean the big storms will get more intense? The jury is still out.
What's going to happen in the next 100 years is still an open question. But it's clear that climate change can modulate hurricane activity. We're clearly influencing climate. How we're influencing hurricane activity still remains to be seen.
And that's getting to the core of the issue. This well-grounded research, way back in time, may help tell us what trouble may be brewing for us in the future. For Science Nation, I'm Miles O'Brien.